Hi. So thanks for coming for the session. So the last week we ended with talking about data frames and in a way how to subset data frames. What are the different options we have with respect to subsetting a given data frame? There may be instances when we want to subset the original data set to get a data set smaller in size, smaller in dimensions, depending upon selection of rows or selection of columns as per the downstream analysis. So we talked about and looked into how we can subset using a logical vector like true and false. And if we subset based on setting criteria on one specific column, we can get a logical vector and can use that logical vector to subset the original data frame. We also looked into options, how we can pick up a particular row or pick up a particular column. And the columns can be picked up in form of a data frame, or it can be form of a vector. So generally, if we are doing logical subsetting, then we would prefer to be in form of a vector. Then you can do a logical test on it. And based on that, you can then do the original data subsetting. Any questions anyone have from the last week, what we discussed? And then I can give a brief explanation of what is, if anything is not so clear. But that part is really, really important. Subsetting the data frame. And today we will be talking about a little bit more about merging of data frames. And this part is going to be equally important because those are some of the steps you will carry out on day-to-day basis when you're doing the data analysis. Irrespective of the nature of your data, there will be always you will be doing subsetting or merging your data with the new data sets or adding new columns, adding new rows. You possibly have instances when you would like to merge two tables or two data frames side by side. So basically, there are some additional information about our observations we want to add up to the existing table. That could be an instance, and there could be chances when we want, there are two tables. For one table may have, let's say, for example, we have information about certain clients, and those clients are from 1 to 100. First 100 clients, and then we have another data frame, or let's say for we have client information for year 2021, and then we may have another data frame for client information for 2022. When we are going to merge those two, we are not merging them side by side, but we simply like stacking them up, which basically is something like the information or observations from year 2021 would be the first 100, whatever the n observations, and followed by we will be merging the second data frame. So this is going to be more like a row by merging. And when you add additional information to the column, that's more like a column wise in merging. So we'll see those kind of examples. And so those are some of the key things we will be looking at. Some of the other things we'll look at is, let's say, if two data frames we are trying to merge by side. So basically, they have the information about the same individuals. Let's say we have one data frame which we have clients or anybody is like clients phone numbers or their locations and other kind of informations, and the second data frame have their, let's say, what are their preferences with respect to certain things, like for example the color choices or the games they prefer, and so on and so forth, and we want to merge them together. So that will be like side-by-side merging. And sometimes it's possible that in our one data frame, the observations are more than the observation in the other data frame. Maybe we are not able to collect information for all the individuals. That's quite possible, or could be the other way around. And it will possibly see these kind of situations arising quite commonly when you're trying to do analysis of your own data sets. So I will go in that one. Briefly and try to look into how we can merge tables in R. But before going into that one, I just want to check with you all guys that you are okay with respect to subsetting the data in terms of rows and columns, or in subsetting in a smaller data frame from the larger one. So any questions so far anyone has with respect to what we have discussed so far right from the beginning? Because these are really crucial things. Manipulating data frames is going to be really key component of your analysis anytime you're going to be moving into R. I will talk about list and other things. Those are mostly not too many people. You will be using those, you can say, data objects as a part of a deeper analysis. And talk about why lists are more sort of an used in deeper analysis, because you can hold all the analysis that step-by-step outputs can be held into a single object, and thus the lists are really useful for that.
Actually, could you review one more time the how to say to subset? Say you want the values, greater than 2 or something like that.
Sure, I'll do that. Okay, so I'll just create the objects what we created before. So it's pretty much the same exercise. So let me create this one. Oh. Because this will be using downstreamly, so let me do that. There's one more thing I want to create is, one second. Okay, so let's say I'm going to pick up, let's say, chip 1. This is the most, I think, typical kind of data frame you will encounter. Or did we add row names too? Something chip 2. So let's see how the chip 2 looks like. Okay. Wow, did we add chip? Let me get hold of a good data set so it's easy. Yeah, XYP. Oh yeah, okay, that's fine. Okay, now I'm going to change the column names maybe a bit better. And now we have chip 2 looks. Okay, so this is less our data set what we have imported, and that's how it looks like. So let me print it out one more time. Okay, so this is let's say our data set, and we have here row names, and then we have column names, a gene ID, chromosome, and positions and enrichment. So let's say we want to pick up. In this case, we want to pick up based on, let's say, the enrichment values. We want to pick up anything which is greater than 3, and all the genes whose enrichment is greater than 3. Those are the ones which we are interested into and downstream analysis. So the first thing is we have to somehow test which all the enrichment values are greater than 3. So let's first extract out just the enrichment values. So what we are going to do is, let's say these are enrichment score. We are going to create a vector called enrichment score, which is nothing but holds the values from enrichment column of our chip 2 data set. Since we want the output in the form of a vector, we are going to use a $, and we are going to use the enrichment. Okay. So this is going to select, only print out or outputs the observations of enrichment column, the last column, and in the form of a vector rather than a data frame. So let's look at how the ENR score looks. Right. So then, which is enrichment score. So yeah, so we have everything in the form of a vector. So the next thing which we want to do is to test which all the values are greater than 3. So before storing those values in a vector, in any, not storing it in a variable, we just simply let's check which of the enrichment scores are greater than 3. You can have 3.0, or if you write even 3, they both will work. So yeah, so it's going to tell us, okay, there's only 2 observations, like 3.5 and 3.4 are the only 2 observations that are larger than 3. So we just want to subset those ones. So what we will use is we'll use this information of false, false, true, true, and subset our original chip 2 data set. So before doing that, let's store this one into a, we can do both ways. We can do without storing, and we can do with storing into something else. So what I would do is I will try to show you with both ways. I'm just putting a logical, you can put any name whatsoever. I'm just giving it a name, the output to where these values would be stored. So now if I look at logical, vector is nothing but the same information in a variable. Here, the information is directly printed out on the screen. We can do both ways. It doesn't matter. So let me go down and we'll see first option in which let's say pick up chip 2. So that's our original data set. Now we are going to subset based on the rows. We are looking at which rows the value is greater than 3, right? In the which rows in enrichment column, the values are greater than 2 or greater than 3, okay? So let's do that one. So we can say chip 2 subset, and we're going to put columns. We can put a comma. So before comma, we are going to specify which rows we want. After comma, we specify before comma, we specify rows which we want. And after comma is the columns we want. Since we want all the columns, the only thing we are subsetting is based on the rows. So we're going to put our information in the row set. And what we are putting here is nothing in which all places the enrichment score is greater than 3. So I'm going to just copy this one, Command C, 1V. This is one step. So in this case, if you're doing something like this, then you're not creating this logical vector. It's everybody's personal preference. There is both of the ways the thing is going to work, or basically the subsetting is going to work equally efficient. But this particular is personal choices, whether you want to create vectors and keep annotating everything as you go along, or you want to do much more, you can say concise or a compressed coding. So it's a personal choice. But the output of this particular the output of this code over here is we have done already. This is the output for that one, right? So this is the code, and this is false, false, true. So basically, that's what will be applied on the rows. So it will be the first row false, second row false, third row true. We want that one, then false, false, and true. And so that kind of logical vector will be used to subset it. So let's see. So that's what happens. So the NA will be picked up because it cannot do any testing on it. So ideally, if you're doing that one, you have to clean up the vector. We have to clean the data frame before. So remove the NAs, and then whatever we left with, we try to do it. But here I'm just trying to show you how to go about it. So it picked up only the ones where the basically enrichment values are greater than 3. Okay, we could have done the same thing rather than doing the testing right over there. We can just put the logical vector, which also hold exactly the same values, true, false, and we can do both ways. So both ways are equally good. I mean, it's as I mentioned before, it's pretty much like our personal preference. What you like to do much more concise coding. I would say just when you're starting with, do as much more descriptive coding as possible, so that when you're visiting it, everything makes sense. As you become more comfortable, you can go into make much more nested coding. This is called the nested coding, in which you put the function inside function inside function. So the innermost function executes first, and based on that, the outer will execute it, then the outer will, and so on and so forth. So in a single line, you possibly can write a code equivalent to, let's say, 5 lines. That's possible, but that needs a little bit of understanding. At the same time, when you next time coming, they will nested you can say coding becomes a little difficult to interpret when you later visiting it, but could be like save you space or something like that. But otherwise, yeah, is as I mentioned, try to do as much descriptive as possible when you start with, but later on you can basically basically go into more nested kind of coding. So does this explain everything, or do you want me to show something else in this one?
I think that's good. Thank you.
Okay. Yeah, you possibly how to get rid of the NAs. So you can possibly first get rid of NAs by using exclamation mark is.NA, and then get rid of those rows, and whatever is left, then you can subset it. So then you will not see this NA row over here. So that part we discussed over there. So, but I can just simply go back and show you this chip 2 and is.NA. So we are checking which all columns are having NA, which all rows are having NA, and where. That is in the enrichment column. So we can say chip 2 $ENR. So, oh, sorry. This is only going to select the columns, basically rows which are NA. We don't want that, which are not NA. So we put a exclamation mark. This goes the other way around. And whatever the output is, you can save it into another, let's say, chip 33 or something like that. I'm just, and now if you look at chip 33, that doesn't have an arrow. And now this one you can use to like the way I described, the same sort of subsetting you can do. In that case, you will get a much cleaner subset of your original data frame. Okay. All right, so from here we will go down and basically look at let's see how the chip RN looks like. Okay, that looks cool. Okay. As I mentioned, so any other questions anyone has, please ask. So if you have anything, I'm more than happy to go back and explain something. But these are really crucial if you're doing with the R. The next thing we are going to look for is merging of data frames. Okay, so let's merge two data frames. One data frame is chip RN. That's one data frame. And then we're creating another data frame here, what we called as EXP. Let's say some expression values in the form of counts we have. And so we have enrichment scores. Now we will also have the expression level of these genes in, let's say, that particular data set. And if you look at it, this is the expression data frame what we have created. So right now, the problem here is that chip RN doesn't have the gene IDs. So let me create chip RN. Yeah, okay. So we're going to merge expression data with chip RN. So this chip 2 is the one which we just created, adding, I cleaned the screen, but that has those row names over here. Why we can't merge this table versus this table? Primarily because there is nothing common between these two data sets. I mean to say there is no primary key. So the values which we are going to use to merge between two data sets are called primary keys. And in this case, we don't have any column that can act as a primary key, because here we have gene ID values and here we have gene, basically sort of like numbers, which doesn't, so nothing is common between them. So we need to have something acting as a primary key to merge them. Now between EXP and chip RN, now is a new, whatever, just a new data set. Chip RN has a row which has the gene names, same as the gene names under gene ID column in EXP. So we can use these two columns to merge these data together. Now here, I think it looks like these gene IDs are in same order between the two data frames, but that is not necessarily to be in that way. You can have the values in the two data frames arranged in entirely different manner. Doesn't matter. R will go through it and then merge those two data sets together. So this sorting is in the same manner is not really the requirement of it. Okay. I'm just going to recreate, just put those data sets again, and I'm going to merge it. Chip RN. Okay. The function what we will be using here to merge these two data frames is going to use base R's merge function. And if you do question mark and look for merge self file, you would possibly get over here. Okay, so here is the how you use merge. Merge is X comma Y. X is your first data frame, Y is your second data frame. So those are two data frames we are trying to merge. And then we are going to specify some values by dot X, which pretty much like which column of X we want to use to merge and which column of Y we would like to merge. So we have to specify in both data sets what are their columns that has to be specified, has to be used for merging. Then we have all equals to false, and we have all dot X and all dot Y. So what they mean pretty much is sometimes basically I maybe let's go first do the first merging, and then I will come by what all dot X and all dot Y means, and that will make more sense once we finish this one. So let's we're going to do is merge. So the function is called merge. Then we have to specify X comma Y. So which data set we want to look at first? We are going to say chip RN. Okay, that's our X, and our second is Y is EXP. Now we have to specify which column of X, which is chip RN, we would like to use to merge. Now in this case, in chip RN, it's not a column, it's a row name. So if you're specifying merging using a row name, you have to give it as a 0. In second case, we are merging by row, basically a column name. So the column we are using, so basically the row names of chip RN, we are merging with column or gene ID of EXP. So we're going to specify by.y to be gene ID. So those are the two column value. Basically, those are the primary keys we are using to merge these two data sets. Let's go and do it. And you can see that this pretty much has been, so they've been merged. The only thing that has happened is now row names has become one of the columns in our new vector. That's going to happen. So, and if let's say to this one, if you want to merge, let's say another data set, so we have another data set which we would like to merge. So let me create another data set over here. And this could be some sort of an information on our same genes. So I'm just going to create it. Okay, let me write down here. So I'm just creating another data frame this time. And rather than having these values, let's put some other values. Let's say rep 1,4. Rep is like repeating values. So I'm going to repeat 1 4 times. Then I'm going to repeat 1, or basically that's another value, maybe 2, 2, 2. That is 2 is repeated 2 times, and rep I'm going to do, let's say 3, how many? 4 plus 2, 6. So we need another 4. So this is going to be created like this. It just created another vector, nothing new, exp new, basically created a new data frame, exp new. Now this one is repeated 4 times, 2 is repeated 2 times, 3 is repeated 4 times. So I just created another data frame. Now I want to merge this xp new with the existing, let's say whatever the output of this one is. I haven't saved that. So that's basically, in order to have that output for merging, I have to save it in some object. So let's say chip 22. That's chip 22. Here, just going back, so here we did simply the merging between chip RN and EXP, okay? And the output is here, but the output is being produced, but I cannot use it for the subsequent merging because it doesn't exist. So I have to save it in with some name. That's where the output will be stored and will be assigned to a variable. Here it is assigned to chip 22. So now this is the output of that merging. I'm trying to merge one more data set. I end up getting some more information, let's say, regarding this. And so I want to merge that also. So let's do this merging. So going to do again merge. We can have anyone. So I'm going to use chip 22 as our X vector and exp new as second, or the Y, and then we can simply say by.x equals to, in this case, the primary key is chip 22, that's our X, the X value, the primary key is called row.names. That's what I have to use. So I'm going to say row.names, and our by.y equals to gene ID. Run this one, it's going to merge that, and then it's going to go an additional column. Oh, okay. Right. The problem happened is why you get expression.x and expression.y, primarily because the exp news column head name is also expression, and this is also expression. So in order to differentiate which belongs to the X, basically chip 22, and which belongs to the Y, which is exp new. It has actually added an additional .x and .y just to differentiate between which one has come from where. So it's try to maintain the column names as different as possible when you're merging these data sets. Any questions here anyone is having? So this is we are merging additional informations. So this way you can keep on merging different data. If you get more and more information about the same individuals, or you can say same observation primary keys. So if you're getting more information about ALD1, then you keep on adding those ones. But if you have like new gene, then you have to add them by row. So that we'll see a little later, but I want to make sure that this is a data frame to data frame merging side by side. And I want to make sure that everyone is has got this one properly. So then I will go to and maybe start showing how the row merging is done. Everyone good? Okay. So the next thing, okay, maybe I just want to show a few other things. So let me create two data frames to show something really, which is by all.x and all.y, and all is going to make a sense. Okay, so just bear with me. So I'm going to create a couple of data sets to demonstrate what I'm talking about right now. Okay, so let's say we're going to merge exp and exp new, and in one case we have values called expression 1, and another one we're going to call, let's say, expression. Let's have a full name as expression. I'm going to remove the first two values from here. So let's make it a little smaller. And let me get rid of these ones. Okay. In this case, what I'm going to do is going to remove, change a little bit here. 4, and this is going to be 2. So I'm going to repeat the last two. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So get rid of these two. Okay. Let's look at these two data frames, and we try to merge these two now. Okay. So let's have a look at those ones first. So I created this one. Control. So let's have a look at these ones. EXP. So EXP is this data set, and another one is exp new. That's the second data set. All right. This is you may encounter scenarios like this, that there's few genes which are really unique to exp. There are few genes which are really unique to exp new, but then we have some genes which are common between the two. So let's now use the same merge method and see how the output looks like. Okay. So let's say expr, so merge, and we're going to use exp, comma, exp new, comma, by.x. So in this case, both the columns has, say the primary key names are same. So I will show you two methods in which you can do more. Again, as I said, this will produce the same results. Maybe let me see, by.x equals to gene ID, comma, by.y equals gene ID. Let's stick to this one, and this is otherwise going to become too confusing. So yeah, the first vector is exp, second is exp new. The first one has a gene ID column. That's what we want to use to merge with the gene ID column of the second one. So in both cases, it's just the gene ID. So let's merge it. And now what you see is only the common ones are displayed, right? So the keys, the ones which are not common between the two, they have been has not been included in output results. So it's sort of like an intersection. Okay, what we are getting is the intersection of exp and exp new, basically what is common between the two. So we may have a scenarios that, okay, we are interested into all the genes which are there in exp, we want to have all those genes. Those results are really significant. If you can pick their corresponding values is fine, but if they're missing, we don't care about it. So we want all of the, you can say, all the genes from EXP, but if there some of the genes don't have values in EXP new, we don't mind it, but we want all of the gene IDs or genes in EXP. Okay, so we're going to run the same merge function again. So we would say merge exp comma exp new, and this time by dot x equals to gene ID. Pretty much the same function I'm writing. There's no difference here. So by dot y equals gene ID. I think the only thing which we're going, so now we want all of the values in X, right? And so everything in X we want. If the corresponding Y comes up, great. If it doesn't, we don't mind that one. So we're going to say all dot X equals true. So you want all of the X values. And now if you look at the end output, so it outputs the common ones. So all the common ones are there. But these two genes don't have their information in EXP new. So those will have any value associated to that one. So this way, we picked up all the basically values of EXP. Similarly, we can do the merging where we, let's say, all that Y equals to true. Now, in this case, what we are interested into, we want information regarding all the genes in EXP new, irrespective if some of these genes don't have value in EXP, that's fine, but we still want to retain all the names or all the genes which are there in EXP. Then we can say all that Y equals to true, and the output will be, now here there are NAs over here, because ALD1 and ALS1, which are in basically EXP new, ALS1 and ALD1, they don't have a corresponding values in EXP. So those, in that case, those has been replaced by NA over here. Okay. So hopefully you're getting the feel of what we're trying to do. So I'll explain one by maybe a little bit with the paper and pen what is happening. So the final one is when we can say all equals to true. So that basically means is we want all the genes from EXP and all the genes from EXP new. If they don't have corresponding values, we just don't care. All the genes should be there. So if you look at this one, now we come back to 10. These two are missing in EXP, and these two are missing in, so these two are actually, the lower two are missing in EXP, the upper two are missing in EXP new. So that's how we can get, we have all the genes from EXP and EXP new, and if they're missing in each other, we are having NAs in their place. Hopefully this explains. Otherwise, I'm just going to go brief, give some just a brief explanation actually what is happening. So let's say we have one data frame which has certain number of values. So this is, let's say, an X, and we have another data frame and Y. Okay, when we are simply merging in the default mode, what we are getting is just these ones. This is a default mode. That's where the first one, when we looked at here, in this one, we didn't say all or anything else. Only the genes which we got was common between the two, basically common between both X and Y, right? That's what we got. When we say, sorry, all dot X equals to true, then the output is something, you can think of something this way. We are getting everything. So we are getting all the values of X, and the common ones we have, their corresponding values are picked up. When we say all dot Y equals to true, then in that case, we are picking up values like this, all the values of Y. If they have a corresponding value in X, we'll pick those up. But if they don't have, we still have the values of Y. So we're getting all the values of Y. When we are saying finally, when we said all equals to true, And what we're picking up, we're basically picking up everything from both the data sets. The common ones are just represented once, but the values we are getting is from both the data sets. The values are from both of them are there. So that's the difference between the 3R, or basically the 4-1. The first one was we're only getting the intersection. The second one, we are getting basically all of X, all of Y, including the common in both cases, and all equals to like everything what we have in the data set. Now, these I have, there's a package called dplyr, and that's quite commonly used in data science, and people, they have a really funky names associated with those ones. So you will call them as inner joins, inner dot join, and there will be a left join, not joint, left join, sorry, and then right join. And there is, I think there's one more, I don't remember that one, but essentially they achieve the same thing, but in a different sort of like a code. Hopefully that means, so if you think about this one was the default one, only the common ones were picked up. All dot X, that's the left side of the circle or the left side of the set we picked up, including the common values. All dot Y, the right side set, the circle with all the values of Y, common ones if they exist. And this one was pretty much like everything, all the values we want, all the genes we want, including the common ones as well as the ones which are unique to both the data sets. Any questions here with respect to this before I go to the further explanation, like start merging with rows and columns? Okay, if not, that's great. Okay. So the first thing what we're going to do now is we're trying to do a merging by, let's say, rows. Okay, this one we have done. So maybe line number 146, that's where we are going to go from. So we are going to merge add new rows or add new columns. Oh, sorry, I missed something actually. I missed by a row somewhere. Oh, no, it's here. Okay. Right. So let's say the existing EXP vector is this one. Oh, data frame is this one. Sorry, not vector. Data frame is this one. And I want to add a new row to it. So let's say I found another gene VIJ08 and its expression value is 23. And I want to add to the existing EXP. The only way I can add is to create first a data frame containing this data sets. The reason behind that one is because the two values which I'm going to add are of different nature, or basically different classes. This is going to be a character class, and this is going to be a numeric value. Since there are two different types, I cannot put them into a vector and attach it. The only object that holds two different kind of data sets or two different classes of values is only a data frame. Not only a data frame, a list also does it, but right now we think that data frame is the only one which holds these two together. So what we have to do is to first create a data frame for just only one gene, and that's what we are doing here. So Control Enter. So what we are doing, creating a data frame called new gene, whose gene ID is this one, whose expression is this one. So exactly the same way that the names are. So let's look at what new gene looks like. New. Keep typing in wrong places all the time. Okay, let's look at new gene. Okay, so this is a new data frame. Okay, has a character chromosome or whatever the gene ID here, its expression. Now we are merging this to the existing EXP table. Now this is basically like stacking one above the other. This is a data frame with only one value. If you have multiple values which are not listed here, we would be doing exactly the same way. So let's do this one. And the function we are going to use is called rbind. R is for row bind. We're binding the two data frames using their rows alongside their rows, if you think about that way. So let's do, so we're going to say rbind. And what we can do, rbind, and the function is here, basically, pretty much. Let's copy that. And what you can see now, we have added this value as an additional row here. We could have an example where we possibly, let's say, I want to add which has more than this number of rows. So let's create another one, maybe new gene 2, and we have multiple values over there. I want to give as many examples as possible because these are really crucial, important things to understand when you're playing with data frames. And you would be, if you're analyzing your data quite a lot, this will come across very often. So C, and let's say we name it maybe 9, and then change the expression. Another one, you can say CIS 12, some values I'm just putting GRM 34. So these are some new names, and these are their corresponding expression values, 23, 20, 22, 102, some random values. So this is nothing. So here I'm not doing anything. I'm just creating a new data frame with 3 new elements to it. So let's say I'm missing a comma. So anytime you see a plus sign, you hit return and say plus sign, that basically means you're missing something to complete the function. And this time it's not really is not very happy that okay, what I'm doing mistake. Okay, this is a string, so it's telling that it cannot identify what it means. So let's say new gene2, and now it's a new data frame. I just created a new data frame. Now I want to merge this new data frame to, let's say, exp. I will use exactly the same function. So let's say I'm going to go back the function which I used, rbind exp with new gene2. This is the new data frame. This is the existing one. I'm just merging those two, and that will get added up at the end. So you can see these two are added over here. So this is like, you can sort of like stacking one data frame above the other one. Okay. Control. Okay. The next thing is, let's say we want to add an additional information. We can do data frame binding. One thing is, let's say we got some cell cycle related information about these genes we are interested into, and we want to add that information to an existing data frame. So let's say this is our cell cycle information. These are the different genes and what stages they are. And this is chip 11. Okay. I'm not sure if that even exists. Chip 11, it says chip 11. We did never create chip 11. So, or maybe not today we have created. So maybe let's use chip 2. Let's see how many values there are. Oh, there are 10. So let's have chip 2 here. So this is chip 2, and this is the cell cycle information we have for each of those genes. Okay. So these are the 6, 9, and 10. Yeah. So this is the information about the cell cycle of the genes, and this is available as a vector. So how we add an additional vector to chip 2? There are 2 ways we can do it. One is using cbind, like rbind. It's a column bind. We are binding another column to the existing vector. And the way we can do it is we use the function cbind. Now, I'm not assigning these values to variable, but that is a good practice that when you do an operation, assign it to a variable and store that value so that we can use it at a later point of time. So that's generally is basically a good practice. So I'm chip 2, comma, cell cycle. So ideally what I would like to do is, let's say this is a new data set, chip 222, which I created after adding one more extra. And what happened? Okay, so one of them has more values than the other one. So I think the cell cycle is little bit 3, 6, 9. Yeah, okay, there are 12, 11 elements. So I just remove one of those ones. They need to have the same number of values, otherwise it's going to complain. So that's why, because they have to merge all the rows of our data frame should have the corresponding values. If any one of them is not having the values, is going to complain about that one. So that's why I have one extra value in cell cycle. The initial vector I created that has 11 elements, but this one has only 10, so it wasn't able to do it. Now, if I do chip 222, I will see that now the cell cycle information has become a part of the existing data frame. So this is the way you can add an additional column to the existing data frame. There's one more way you can do it rather than using cbind. For some reason, if you don't like to use cbind, there's another one which we can do. So that is like, so cbind, the output you have to store into a new vector, right? So the output of this one has to be stored into a new variable, not a vector, sorry. The output of this one we stored into a new variable called chip222, right? But let's say you want to just add the column to chip22 without writing it to something new. You just want to modify chip2 in some way. So the way to do that one is you can say chip2, and you specify what column, what new column name you would like to have it. So let's say the new column name that we would like to have to chip2 is cell cycle. And what values we would like to have. So either you can specify this vector over here. All the values you can write as pretty much do it this way. Okay, this way you have all the values, or we already have that all those values are stored into a vector, same thing, in a variable called cell cycle. So I can simply write cell cycle. And now if you look at chip2, chip2 has an added data, had an added column called chips cell cycle, and the values of cell cycle comes from the cell cycle vector, which was over here. Right? So these are two different methods. In this case, we don't have to store into a new object. A new column has been added to this one, and you can try whichever way method works for you, and you would like to use. Both of them are particularly good. There is no issue with either of those ones. Any questions here?
You said there is a function rbind and cbind. What is the difference?
So rbind, we are adding two columns, two data frames, row by row.
Okay.
A cbind, we are adding a column, basically new data, new values to the data frame. So if I sort of like explain, just I'm sure you got it, but just try to explain what it is. So let's say our existing data frame is this way. And what are the three different columns in this case, and we may have X, Y, and Z. These are our row names, R1, R2, and so on and so forth. And maybe this is R5. Okay. If we are adding a new values to our data frame as rows, let's say if you have more information over here and we want to add an extra rows to it. So let's say X values are like 1, 2, 3, 4, 5, and here is M, M1, M2, then C1, C2, C5, and this could be again like 22, 21, whatever the values this could represent, so we don't know, at 119. And now we have new values we say we have gathered, and we know those values as let's say could be 19, could be 20 or something like that, and those are X. In this case also these are X, Y, and Z. And this could be N1, N2, and this would be 13, 75. These are values. Now, when we are merging this data frame, this is also data frame. Why we can't use any other way is because this is a numerical, this is a character, and this is a numerical data. Numerical, character, numerical. So they have, the only way you can have all these three values and still have their same class is to have in data frame. If you put them into a vector, they all will get coerced. So all they will be get converted into a character. We talked about coercion if we have mixed type. So the only way to hold that one is to have basically a data frame. So this way, this is our data frame 2. This is our data frame 1. And if you are merging those two together, the function we will be using is rbind, binding them by the rows. So we are attaching, like stacking one over the other. Now to the whole, let's say if we have another to df1, we want to add an additional information. Let's say we got some other maybe n or maybe let's say m, we have another values, and those values are we want to add by these are present in the form of a vector, though I'm writing like this. So and these values could be anything, maybe true, false, true, true, false. When you are adding these together, you are adding a new column to this one. So this is referred as cbind. One is R bind, another is C bind. We are binding by rows and we are binding by columns. So that entirely depends. So these two will be binded together. Okay. If you want to bind after creating this whole thing and then binding this one, then we need to have another two more values here. Otherwise, it will not be possible. Okay. So this here we need to have the same number of values here as the same number of rows, the same number of rows you have in the rest of the data frame. Does that make sense?
Yes.
Okay, cool. Yeah, so that's pretty much what I was meant by R bind and C bind. There's nothing specific to those ones. Yeah. Let me see. So then again, we talked about these three different methods. Where what's the default is? Default is just the intersection. If you say all equals to true, then we are getting everything, literally left, right, common as well as the unique from both the tables. All dot x is common plus everything of x, and all dot y everything of common plus everything rest of the everything of y. That's how all dot x and all dot y end up working that way. So this is pretty much the merging of tables, and this is sort of like really important to have it, some idea about it. Most of your analysis, you would be pretty much circulating around this concept of either creating data frames, adding new rows, new columns, subsetting data frames. And once you have done that, and the reason we would be doing so much of is cleaning up your data frame. Irrespective of from wherever you're getting your data frame, invariably there will be some issues with it. Could be missing values, or could be values from certain places that you don't want to include it, or you want to subset it in some ways that you have information based on the question you are asking. So you have to subset your original data frame and then do a downstream analysis. So a lot of time you will be spending in cleaning up your data frames. Once you get your data frame clean, then it's pretty much really straightforward whether you're going to do visualization, or if you're trying to do building like models, regression, logistic, or any kind of machine learning algorithms. If you're running it, those are pretty downstream process of this one. But the key thing is a lot of time is spent by on cleaning your original data frame, and a lot of time spent also to understand how each variable is represented in data frame. So these are like 10 rows we are looking at, but there will be scenarios when we have like hundreds and thousands of rows and basically another 1,000 columns. So need to get an understanding what values are in each of the columns and how each column can be related to the other columns, like correlations and all those kind of things. We might be interested at a certain point of time before we start building models and other things. So we're pretty much close to like 6 minutes are left. So I don't want to start anything new, and I didn't end up sending some new material. So I will make, the first thing I will do is send you information, basically material for the next class. So next class, we will be talking a lot about lists and metrics and arrays. Lists are another kind of, you can say, data objects, which in R, which stores literally any kind of object of an R. An R, you can have the same, the list can hold simple variables like numbers, characters, or anything. At the same time, it can hold a data frame. So you can store a data frame inside a list. You can also have a list inside a list. So those are, so list is very, very different from data frames. They are in a way, you can say the mixed data type. If you look at objects with mixed data type, having numbers and characters or anything else, data frames are the most structured ones. Basically, they have rows and they have columns. They're very well defined. When you look at the lists are not really that well. They are well defined in their own way, but it's basically what I say is they vary a lot, kind of, you can say the values they might be holding. So the simple way of creating a list is you use list, function list, and you have parentheses. Inside that, you specify different values. You can have a number 24. You can have a character name, whatever you like, David. You can store the same thing. And then you can also have in the same, you may have a place where you want to store a data frame called df. There will be a data frame you can store. You can also store, let's say, an array. Array is like a numerical values, n1, n2, n3. it can have arrays, and you can have, like, as you can see that this is numeric. You start with this character, you can have a data frame, you can have an array. So list can have literally anything, but there's a structure in a way that, yeah, you can retrieve all these values, but they're not as structured as data frames we would be interested into. Now, why we would have to have lists? When we do downstream more analysis or trying to look into using R for in packages, so you will come across two terminologies, basically two type of data objects in R. One is called S3 class and another is called S4 class. The S3 class is an older version of storing values, different kind of values. And S4 is a newer version. It's a little bit more structured, and the way you retrieve the values is a little bit different. Now, and S3, I think, pretty much works very close to the way the lists are working. And what's why we need to have these kind of information is, so let's start with, I'll give you an example why we would like to have. So let's say we start with a data frame, not a data frame. We got some RNA-seq experiment, or proteomics, or any kind of data set you are doing. So we have sample 1, sample 2, and then we may have a C1 and C2, another 2 samples. We may have, let's say, gene 1, gene 2, and gene 3. Okay. Now, when we start doing these analysis, so this is going to be our starting data set. So this is our, these are our columns, these are our rows, that's fine. Now we want to normalize our data. So in the way, there are different normalization methods generally used depending upon what you're doing. So, for example, DESeq2 has its own way of normalizing data. AdJar has its own, and NoiseSeq is another package which can, when you don't have replicates, that's what you have to use. So everyone normalizes the values in each sample differently. So what we will have is something called scaling factors. Scaling factors are nothing but the numbers we will be using to scale up the data or normalize the data, so that we are not using unnormalized data. Once you have done that, you're going to possibly call differential expression of samples. So you will get list of genes, let's say differentially expressed results, let's say. That could be another, you can think of maybe a data frame. You may end up also doing sort of like PCA analysis. Okay. You may also end up doing a transformation of your data. So transformation of your data could be in the form of there's RLog, RLD transformation. There is a VSD transformation, generally commonly used in machine learning or possibly in data science. And so what we are seeing here is at each step, we are gathering different information. Yeah, we can store this information in different variables. So let's say this is an A, whatever the A variable. We can store this is in B, can be C, this is in D, and this is E, F, and G. Okay, maybe not this one. So we have like, but every step what we're creating the information is pretty much independent of each other. They're scattered around. We would like somewhere that we can store all this value together. So that's why the lists are quite useful. In list, you can store all the column names separately. You can store these row names separately. You can store this basically what you can say the values or expression values, what we refer as counts or count metrics. We can also store scaling factor, and they could be all different types, DE and VLD transformation, not VLD, VSD transformation, RSD, PCA. So all kind of different data sets we're storing into one single object, and we can retrieve it anything we would need from here for our downstream analysis. So that's the primary reason why lists are quite useful. So as we keep on going through the analysis, we can store our information as we keep along. So that everything is at a single place, and we can retrieve as and when we need it. So this is a brief introduction about that. So this will discuss in our next class when we meet it. But for time being, I think this much should be okay. I'm going to stop the recording.